All right, good evening, everyone. Doing a quick recap of optical isolations. And how we detect it. So isolations, and then I'll just do recap, see? Recap. And then C2, 11, C26, so 11:55 p.m. Anyways, so let's talk about optical isolations of, say, a biologically mixed group of molecules. And to start this off, I will bring in an image from Wikipedia, which is a polarimeter, and a quick description of how it works. It literally is a regular non-polarized light source, such as an incandescent bulb. A little confusing here is that these panes are actually supposed to be figures of what the light is. And so 2 is the light is shown having all directions, and 4 is it's having one direction, and then 6 is having a rotated direction. So these are actually representations of the light itself, and these are the instrument, which is the polarizer, the tube filled with solvent, and a chiral molecule or chiral molecules. And this is a rotatable polarized lens. And so kind of like what you find on a pair of fancy sunglasses, and 8 is the detector. Usually an eyeball, but more importantly, we'll describe what that would probably look like if we'd have an intensity graph of some sort. So let's go ahead and get that started. So let's see. Let's say we have molecules A and B. So you'd have a intensity here. Intensity. And I go say, let's just say it's arbitrarily up to 360 degrees, but it's probably going to be somewhere in the middle, right? Intensity, and then this is for chiral molecule A, and then we'll have another one over here for chiral molecule B, some biologically produced sources. And then so at, say, some angle here, you'd have low intensity, low intensity, low intensity, and then you see a little bump in intensity at this rotation here. I'll just arbitrarily say it's 15 degrees here. And then on molecule B, dissolved somewhere in this vessel here. Let's say that one is going to be like this, and then get a bump like this at say 60 degrees, whatever it is. The actual amounts, I've not actually done this myself in a laboratory, so I'm not really positive what the amounts would logically be, but those would be rotations of item 7 to get the peak of intensity where these things are exactly aligned the same amount. And so depending if you had these two in a mixture together, you would have some combination of these rotations. In this case, I have them both the same way. They could have opposite directions as well. Maybe I could describe this one as having a minus rotation, and then we'll say this is that minus 360. You probably have more than 360, depending how many things you got going on inside one of these mixtures, but we'll just say this one's a positive 360, just because, for the sake of argument. So let's say if you wanted to do an optical isolation, you would have to do some sort of chromatography. And so if you had both of them in a mixture together, like this, but we didn't know what the ratios were, so say you had A and B, A plus B in unknown quantity intensity, it would have some sort of peak. Let's say it's 60, let's say it's mostly B with a little bit of A. This would probably bring it down to like, here you can see your intensity like this at say 30. It is some mixture, but we don't actually know what it would be, but you could probably reverse engineer what that ratio is based on what this angle is, if those were the only two chiral components. But yeah, so if you suppose you had this is for an optical isolation, if you had some mixture of these two chemicals that are both chiral but have different rotations. If you have something that's termed optically pure, you would have to have only one of these things created, usually in vitro. Otherwise, you'd have to extract it from a bunch of enzymes or some other mixture of other things. But yeah, optically isolated would therefore have a pure 60 degrees, and then whereas a mixture would have some mixture of two together at 30 degrees, say, of optical rotation, which again is the rotation of this versus your intensity detector. This is 8 here. But yeah, that is this idea is basically well, complete at this point. It's like, to keep it as simple as possible, optical isolations are basically taking a specific enantiomer out of a chiral enantiomer out of a mixture of other chemicals, and then an optically pure formation is something done in vitro of only one A or B. So hopefully that makes sense. Thanks, YouTube.